Today I'm going to look at another electricity and magnetism question, and I'm going to be interrupted periodically as I double check things here. In this case, this was from a test. This is actually from the same test that last week's question came from. And in this question, we're given a circuit that has 3 different EMFs at 6, 12, and 10 volts. And then it has 5 different resistors. And the question says to derive the equations required to find the current in each resistor and then find the actual current. And my marking scheme for this, or my grading scheme, was weighted heavily towards deriving the equations because I wanted I wanted the students to put the effort into making sure that they got the right equations. And in my mind, that's the physics part. Once you have the equations and then you can actually solve them in terms of the current to find the current, that's just algebra. That's just math. It's very useful. You need to do that if you want to actually solve for the circuit, but getting the equations in the first place is the sort of trickiest thing. So my take on that is that deriving the equations was worth far more than actually solving them. And I'm just signing in on my laptop so that I can pay attention to this. So once again, this is a good reminder. Okay, it is showing what I want it to show. If you have questions during the webinar, then please submit your questions through the chat because that's how I will see them. And then I can actually take your questions, and what I would typically do is just talk back instead of replying on the chat. But anyway, this will hopefully work out quite well. All right, so in doing this, we need to actually label the current going through each branch. And this is a rather unusual looking circuit, but it's really not that bad. So I'm going to use some different colors and I'll identify things. And actually, the first thing is that we have to find the current in each resistor. So I'm going to actually just draw an arrow representing the direction that I'm guessing for each current. So for the 20 ohm resistor up in the top here, I will guess that the current is going to the left, and I'm going to call that I1. In the 40 ohm resistor, I'm going to also guess that the current is going to the left. I'll call that I2. And because the 30 ohm resistor is in a straight line there, all the electrons going through 40 have to go through 30, and that will be the same current I2 going through the 30 ohm resistor. Then for the 5 ohm resistor, I'm just going to guess that it's moving to the right. I'll call that I3. And then for the 30 ohm resistor at the bottom, I'm going to again guess that that current is moving to the right, and that will be I4. It's a different current than the other one. Now, there are also quite a few junctions here, and I'm just going to label those. So we have a junction at that point that I will call A, and I will label that capital A. Going around, we have another junction. We don't care about junctions with only 2 wires, for example, one right there. I'm just going to erase that. It just overcomplicates things. Technically, you could call that a junction, but the current in is the current out, and that's how you get the same current through. It's really overcomplicating things. But if I look at all of the different points here, and it turns out that when I solved this, I did have another one. Oh, that doesn't show up at all. So I'm going to label this point, even though there's no junction there. And I just said, don't do that. Just because when I label the loops, I want to actually label points. And this will make a bit more sense. In fact, why don't I just undo that? Forget that I did that for the moment, and it will make more sense when I get to that in just a minute. All right. The next thing then is to actually, or the key thing to find the equations is to use Kirchhoff's voltage law, or the loop rule, and Kirchhoff's current law, or the junction rule, to find equations for this system. And the first thing I'm going to do is actually look at a loop here going clockwise from B to C to B. So starting at B, going to C, back to B, and CW here stands for clockwise. And as I do that, I start at B, and then I'm going from left to right through the 20 ohm resistor, which is against the direction of current that I had for I1. So I have positive IR, or positive 20 I1, and then go down to C, and then I'm going from C to B. That's going from the positive terminal to the negative terminal of the EMF. So that's minus 10, and then I get back to B, and by the loop rule, then that's equal to 0. And this is one of my equations. And I'm going to call that equation A, because first I'm going to focus on deriving the equations, but second, then I'm going to solve them, and referring to the equations by letter or by number helps quite a bit with that. Okay, the next equation, I'm going to go from A to D to C to B back to A, and that's counterclockwise. So here, I guess I would label loop 1, loop 2 is going counterclockwise like this. So this is loop 2, from A straight to D, then to C, then to B, and then back to A. And I don't really need to write counterclockwise here because it's possible to do it, or rather, it's not possible to do that loop in that order clockwise, but whatever, it doesn't really hurt. All right, so in this case, I start by encountering the 5 ohm resistor going in the direction of current. So I have a negative 5 I3. Then I go from the negative to the positive plate of this voltage source, 12 volts. So I have plus 12 volts. Then from D to C, there's nothing. Then I'm going to the left across the 10 volts. So I have minus 10. Then I'm going with I2. So I have minus 40 I2. Then with I2 again, so minus 30 I2. And then I'm going from the negative to the positive plate of this 6 volt resistor, so I'm going plus 6. And then I'm back to A, so that's the end of the equation, that's equal to 0. And I probably mentioned last week, but I'll mention again. I put a box around my final answers just to help clarify to whoever's grading my work that that is one of the equations. That just helps them like basically, excuse me, helping them to help me get full marks and recognize that I know what I'm doing. Okay, there's another loop that we can look at in this circuit, and that's going from A to D clockwise. And you know what? I don't need to have that E. This would be loop 3. Going to A, D, A, and clockwise. So in this case, I start at A. I'm going with I3 across that 5 ohm resistor. So I have negative 5 I3 going up that EMF, so plus 12 volts. Then I'm going against I4, so plus 30 I4. And then I get back to where I started, so that's equal to 0. Call that equation C. And the last thing, I don't have any, there are more loops, but I won't get any more unique or any more independent equations from the loops. I need to actually look at a junction. So I'll look at junction A. In that case, if I just take I2, it would continue going counterclockwise. So I2 is going into the junction. I3 is going out. And I4 is also going out. So in that case, I would have positive I2 because it's going in, minus I3 minus I4 is equal to 0. and that's equation D. Or if you like, in is equal to I out as the totals, then I would have I2 going in is equal to I3 plus I4 going out, which is the same equation really. It's just rearranged a bit so that all the terms are positive. So that would also work. But I'm going to stick with D just because that's how I solved the problem originally. So that's it. That's the equations. And at this point, that only takes a few minutes to do, but you get the 4 equations that you need. This is, I'm going to just make a note here. This is the same equation as D, which is why I say there are 4 equations, even though I boxed in 5 things. And in terms of teaching, from the teaching perspective, I found this was easier to grade because it's a lot easier to see that the students understand what's going on. Whereas following through the algebra and noticing, because it's really easy to make mistakes when solving a set of 4 simultaneous equations or even 3. I've personally much preferred this because I felt that this marking scheme and this grading scheme of weighting the equations higher represents the physics better. It rewards doing better on the physics. And then, of course, because the right answer is important, there are some marks, in this case, 1/4 of the marks, just for solving. Okay, so the next step then is to solve. And I want to have a new page here and then hide that. So once we have derived the equations, which I get by going like that. I should just do it that way, because then I can flip. So once we derive these equations, then it's a matter of solving for the 4 unknowns. Now we have 5 resistors, but we know that I2 goes through both the 30 and the 40 ohm resistor. So the first equation I'm going to start with is A, because that was the simplest one. If we just look back here, we have 20I1 minus 10 equals 0. So it's one equation, one unknown. We can actually solve that right away. So we have 20I1 minus 10 equals 0, which means that 20I1 is equal to 10, and I1 is equal to 10 over 20. Therefore, I1 is equal to 0.5 amps. All right, so then if I look at equation B, equation B was pretty long, but I can simplify. We have I3, I2, and we have 2 terms for I2, so that ends up being negative 70 I2, and then plus 12 minus 10 plus 6. That's 18 minus 10, so we get 8 out of those numbers. So this simplifies quite a bit. So if I start out with the original, minus 5 I3, plus 12 minus 10, if I collect that plus 6 here, then I have minus 40 I2, minus 30 I2. All of that was equal to 0. So I can rewrite that. Negative 5 I3 plus 12 minus 10 gives me 2 plus 6, so I have plus 8. And then minus 40 minus 30 I2, so I have minus 70 I2 is equal to 0. What I'm going to do here, because 5i3 shows up in equation B and 5i3 shows up in equation C, I'm actually going to sort of do a trick and just isolate 5i3. So in this case, I would have 8 minus 70i2 is equal to 5i3. And I'll leave it at that for the moment. Then I'm going to look at equation C. For equation C, I had negative 5i3 plus 12 plus 30i4 equals 0. Then I can actually also isolate 5i3 again. I'm going to get 12 plus 30i4 equals 5 I3. Now, the next step then is to notice that 5I3 is equal to 5I3. So I can take these two things, B and C, both expressed where I've isolated 5I3, and then since 5I3 is equal to 5I3, I can put B on the left, so I have 8 minus 70I2 is equal to 12 plus 30I4. So I still have one equation and two unknowns, but I still have one equation left that I haven't actually looked at yet. And I can simplify this a little bit by, let's see, if I have 12 minus 8, I guess I would have negative 70I2 is equal to 12 minus 8 gives me 4 plus 30I4. And then what I did after that is I just made the I2 positive. So I have multiply everything by negative 1. So 70I2 is equal to negative 4 minus 30I4. The advantage of following along solutions I've already done, I mean, I know you can't do that on the test, but it makes sure that I get the right answer, because when I set this up originally, I actually derived the equations and made sure I had the equations correct. And then I created a matrix in, not in MATLAB, but in like a free version of MATLAB called Octave. And I just used Gauss-Jordan elimination to solve the equations in matrix form. And using Octave, it's really easy because you just enter it in as the matrix and say solve. And I forget the exact term. Sometime I should look that up and show that to you guys. Anyway, that confirms that I do get the right answers. So, because even with lots of experience, it's easy to make an algebraic mistake somewhere in here. It's easy to accidentally say, well, 12 minus 8 is 20, even though 12 minus negative 8 is 20. Anyway, the next thing then is to bring in equation D. So equation D said that I2 minus I3 minus I4 is equal to 0. And it turns out actually then multiply this by 70 so that I can get 70I2 and is equal to 70I3 plus 70I4. And it's funny because at this point, oh, I see what I did here. Then I factor out, because I had isolated I3 in terms of I2 and I4, what I want to do is to solve for I4 in this case. So I have, it's funny looking at this and deciphering what I had done. Right. I have B in terms of I4. So I have this equation. I need to change colors. This equation should maybe get a letter E because I'm going to use this shortly. Essentially, this 70I2 is going to get substituted there in terms of I4. So what I want to do then is to express this 70I3 in terms of I4. And I have this one here. Well, maybe I'll call this F. So if I factor out 5 from here, it turns out that 14 times 5 gives 70. So I have 14 times 5I3 plus 70I4. And I can take this 70I2 and write it as negative 4 minus 30I4. So at this point in the equation, I have I4 and I3, but I can take this 5I3 here and substitute in there. And that will give me something in terms of I4. So I just carry the left-hand side here. Negative 4 minus 30I4 is equal to 14 times, and then I substitute in 12 plus 30I4 plus 70I4. Then I just need to expand. Rather than multiplying, I guess 14 times 3 isn't so bad. It'll be 42. So that's 420. All right. Yeah, it's not so bad after all. So I have minus 4 minus 30. I4 is equal to 14 times 12, which is 28 more than 144, so 168. Plus, and then we have 420 I4 plus 70 I4. So the numbers are kind of big and annoying, but it's not that bad. Then I can actually collect this pretty easily. And what I want is to get the I4s on the left-hand side. So then I have negative 30 and then 420 and 70. That ends up being 490. So negative 30. Maybe I'll just take another step at this. We have negative 30 I4. If I only have two numbers here, negative 4. So if I add 4 to both sides, I'd get 168 plus 4, which is 172. Plus, and then I would have 490. I4. So if I subtract 490 I4 from both sides, I have negative 520 I4 is equal to 172. And so I4 is equal to negative 172 divided by 520. Therefore, I4 is equal to negative 0.33 amps. Okay, so I've solved for two of them. For whatever reason, I only gave myself 1 mark for all of that work. Now, the negative here isn't the end of the world. All that means is that it's actually opposite to the direction that was shown. So it turns out that I4 was actually going to the left. Positive 0.33 amps to the left. Hopefully by the time you're writing the test, you're familiar with that idea that you don't have to go back and redo anything. You don't have to rederive the equations. You don't have to redraw anything. It just turns out that actually I4 is positive 0.33 amps to the left, and you could write as negative 0.33 amps to the right, but that might be a bit confusing. The negative just means it's in the opposite direction to what I guessed. It's still important to guess because you need to guess the directions so that you can write the equations. And you need the directions to stay the same, to not change between one equation and the other, which is why you draw the directions of the current directions on the circuit before you actually derive the equations. Okay. Once we have I4, then we actually have expressions for I3 in terms of I4, and we have an expression for I2 in terms of I4. So I'll start with the I3 expression because it's right here, and then I can erase it after that. So what I have is 5I3 is equal to 12 plus 30I4. When I'm doing the substitution here, I actually want to insert the fraction instead of the negative 0.33 because that will give me a more precise answer. On a test, I wouldn't care. If I was grading and you put 0.33 and there's a rounding error, to be honest, I would not care at all. But if you're looking at a web work or some other kind of online system where it takes more precision than is humanly realistic, then you really do want to put the fractions in. So it's just generally it's a good habit. The important thing actually to focus on is that we got a negative answer for the equations. We got a negative answer in terms of I4 going to the right. And all of our equations were derived with that in mind, that I4 went to the right. So when we substitute in, we have to include that negative. So I put negative 172 over 520 into this equation. And then when I simplify that, oh, you know what's funny is that I did it the other way. Anyway, when I do that, I get essentially end up getting 12 minus 10. So I have 2 amps on the right-hand side, and that's equal to 5I3. That's not actually 2 amps yet. I have to then divide by 5. So I3 is equal to 2 over 5. Therefore, I3 is equal to 0.4 amps. And that one is positive. So that means that I3 was 0.4 amps to the right. Okay, so then it's just a matter of solving for I2, and I'm going to use this equation E to do that. So I have 70 I2 is equal to negative 4 minus 30 I4. And we just actually inserted 30 I4 over here, but I'll just continue. So negative 4 minus 30 times, and again, we have to substitute in the negative 172 over 520. So that's negative 4. But the negatives here end up canceling out. So we have negative minus 10 or just positive 10. So we get 6. And then I2 is going to be 6 over 70. And then I can say I2, and that's a positive number. It's small, but it's positive. I have 0.0857. Maybe I'll just put 0.086 amps. I'm just looking at this and realizing, well, anyway, I'm not going to worry about that. I did confirm these numbers. I think the 0.33 was rounded. It's probably 0.324 or something like that, because I2, I3, and I4 should all add up to 0. Or actually, no, that's not true. They shouldn't. It's not that they add up to 0. It's when I look at that equation D, I2 minus I3 minus I4 should be equal to 0. So minus I3, yeah, minus I4. Anyway, that's basically it. My preferred method of solving simultaneous equations is to do substitution, and my experience with it is that I do have to take things step by step. Otherwise, I know that I personally will make mistakes, and I had to learn that on the job, basically, to take care, to take my time and make sure that each step was correct. So as you get better with this, you will know when you can skip steps. But what I recommend is that if you're not sure, you should write out the next step and write out the intermediate steps. Another way to look at this is that if you end up trying to rush the algebra and make mistakes, then it's a sign that you need to slow down just a little bit and make sure that you get the right answer. In my case, it turned out to be much less expensive to slow down and get the right answer the first time than to speed through it and save half an hour or save a couple of hours and then realize 2 months down the road that there was a mistake and I had to go back, and then instead of saving a couple of hours, it might take an extra couple of weeks or months even to recover from a mistake like that early on. Anyway, that's it for this webinar today, because I don't see any questions whatsoever. And I'm going to keep experimenting with this. I know I'm actually keeping them a bit shorter, so this is 30 minutes long. And if you have questions, then please email them to me. If you would like to attend live and ask questions through the chat, then I can stay longer, up to an hour, and answer your questions directly. And I would love to do that, because as fun as this is, knowing that it can help people do better in physics, it's always much more fun when I'm working with somebody interactively. So I would love to see that. Anyway, I suppose what I should do actually is go back to the website, stop sharing my screen so that you can see me again. So anyway, thank you for watching this video. I really appreciate your attention in this, and I would love to help you do better in physics. So please don't hesitate to send me your questions and ask for help. And either way, good luck with physics.